Okay, so what I'm going to do is actually run through the free fall part. As we didn't get to it in class, I will touch upon it really briefly in class because there's some things I just can't do here, including demonstrations, but this should hopefully help you with the last couple questions on the homework set, which I know I didn't get to. So the big idea for free fall, as we see demonstrated here, is that, how should I say, all objects that are in free fall move under the influence of gravity only. So only gravity. So in other words, we don't have anything propelling like airplanes who have jet engines who propel things and whatnot. Those are not free fall. So under gravity only. This includes dropping an object and throwing an object up, because if you think about it, if you pretend my mouse was a ball, if I throw it up, once the ball leaves my hand, it actually is under the influence of gravity only. So thrown objects also fall under this category. So the main idea, and I'll do some stuff in class, so we're just going to quickly go through this, is that objects under free fall undergo constant acceleration. Now notice I didn't say speed or velocity. In other words, acceleration means it's speeding up. So if you think of an object being dropped, it's getting faster and faster at this rate, 9.81. This is our magic number in physics. Just like pi is 3.14, g is 9.81, where g represents an acceleration of falling objects. We're going to use this in our equations to help us solve for problems like how far something falls, or how long it takes for something to fall, or the speed at which something falls. So this is the main idea. This is not given in most problems. They assume you know this value, so that's kind of tricky. And yes, it's downward, although I'm not going to go too crazy with negative signs, but theoretically, yes, we should imply negative because it is going down. And the cool thing is it's an independent of mass, so all objects, including a feather and an elephant, will actually accelerate at this rate, assuming there's no air resistance. And there we go. Why? Because gravity acts the same in all objects. Well, I should be careful with that. It's the same force that acts on all objects, but it's not the same amount. Heavier masses just get pulled more, and they happen to equal out in the end. I'll show you this video later. It's pretty cool, showing that these objects will actually fall at the same rate. And so when an object falls, it gets faster. Now notice that in every second in this demonstration that the speed increases about 9.81. Now notice it's rounded to 10 here to see it more clearly. But here we are, just like this. It increases speed each time. So we're going to be able to calculate things that fall with these equations. Now it is incredibly important. Let me take some notes here, so give me a second while I set up my pen. My cool fancy equipment here. Oops, I didn't mean to go back. Let's go back. Previous. There we go. Get a pen in here. Go back to our slides. There we go. Annotate. Annotate. Let me see, sorry. Technical difficulties, just bear with me. Should be able to write on this. Interesting. Oh, I know. Oh, that's okay. I won't be able to write on this. That's fine. So anyway, the object is, these are falling objects. You cannot use these equations for other motion. If the object's like a car on a highway, or an object is moving on a surface, like the ground or something. These are specifically from falling. How can you recognize these things are falling, even though the equations look very similar to things we've done already? Is look at this G. G is going to tell you that these are falling because this G refers to free fall acceleration. So, as you can see, velocity is, how fast you are going. G is the acceleration, which will be 9.81, and T is time in seconds. D is how far you gone, or your distance. 1/2 is literally just 1/2. G is 9.81, and T is going to be time in seconds. So, let me actually talk a little bit again. So V equals GT. So a couple notes, G is not given in the problem. You should imply that you know this, or in other words, you could look this up, it's implied. And like I said, these equations can only be used, it's supposed to be a square, let's make that look nicer. There we go. And the keywords, of course, is dropping or falling. These are free fall keywords. Anything that's, signifies that. So let's use these equations just to see how they're used. So I set up the two equations that I have before on the slide. So one of the slides says, how fast does a penny go if it takes 8.81 seconds to fall the Empire State Building? So these are actually real values, so this is pretty cool. And note that this is without air resistance. So air resistance is actually a huge factor. But let's see how fast the penny would go if we were to release it from the Empire State Building. So here we are. Here's the Empire State Building. Here's my little drawing of it. I don't know if it actually looks like this. There we go, not to scale. We're dropping this penny. The question is, what is the speed right here? Now, some of you will say the speed here is at rest. Well, we don't want that because that doesn't tell us how fast it's going. Yes, it does stop when it hits the ground, but we want it right before it hits the ground. So we're going to get a value that is actually meaningful instead of one that is at rest. So what we're going to do is we're looking for how fast. So notice that's a variable v, or speed. Velocity, quite technically, because it includes a direction. And notice that we have a time right here, how long it takes to fall. That's important. So we're going to be using v equals gt, where t is how long it falls. So notice that it's not any time, it's just a very specific time. G is our magic number, 9.81 in physics. We'll use this all through physics, over and over again. And this is how fast when falling. So this is, again, the equation we want to use. Notice that G is not in the setup. So this looks very vacant, right? It looks like we don't have a lot of information, but in fact we do. So the only thing we really need is time, which we have. So let's try that. V is equal to G, which is 9.81 meters per second squared, times the time it takes to fall that distance, like this. There you go. And I have my calculator. Oops, sorry. Right here, 9.81 times 8.81. I get a velocity of 86.43 meters per second. That's how fast it's going. And just to give you a comparison, that is approximately 193 miles per hour. Whoa. So that's pretty lethal, actually. That's the speed of a bullet at that point. But I'll tell you that it actually never reaches that speed because of air resistance. So actually, a penny really will only go as fast as 60 miles per hour. So we won't actually see that in real life. This is what we'll see, which is not fun. It's going to hurt, but it's not going to, be lethal in this case. Anyway, so this is our velocity, and to make it an official velocity, we should imply that it is downward, because we need direction for velocity. A course, I could also imply a negative sign. That would also mean downward, but this is sufficient for now. In your homework, I don't think it really goes into too much detail with signs, so just be careful with that. I have to look at it. But that is the velocity at the bottom, just like that. So, let's move on. Let's take a look at the next question on that slide. It says, how tall is the building? So instead of how far, given the time, how tall is it? So here's the building again. And you're looking for how tall. So that's a distance measure. And in fact, we can assume that if we know how long it took to fall, we could assume that it fell, for that distance. So the falling distance would tell us the height, in other words. So, same idea. This is only used for free fall objects. Now, d is the distance. That's the fall distance. G is our magic number again, 9.81. And this is the fall time. We know the fall time, we will have the right distance, or the right distance. So in this one we have all our information. This is just a number, so 1/2 or 0.5. This is also just a number, and we have time. We have each variable to solve this. So let's go ahead because I only have a few minutes left on this. So 1/2, some people find it easier just to do 0.5. That's fine. You do 1/2. Either way, that's just a number. This is going to be 9.81. And then t is going to be our time it takes to fall. This is the time it takes to go this whole distance, so I can use this time. And we're going to square this number. So I'll do that first, because I usually in my calculator will start off with the square. So I do 8.81 squared. Then I do times 9.81, then times 0.5. My answer is 380.71 meters tall. And that is our official answer right there. And this is the actual height. Sorry, my cursive is beautiful. That's the actual height. Which happens to be like 100. So meters is like 3 feet. So it's like 125 feet tall. Just to give you an idea. Oh, I'm sorry. Opposite. No, 3 feet in a meter. There's that many meters. Divided by times 3. Anyway, regardless, ignore that. The whole idea is this is how you solve for the distance right here. So notice again that G is not in the problem. It's implied. And the only thing you need to find height is time. So that's how you apply this. Now, just side note, and then I'll make another video. If you don't have time, try solving for it using one of the other equations. So you might be given a velocity instead. So you might need to solve time and then plug it into, equation like this. I'm just not speaking to a specific example. This would actually go all the way over here. There we go. But just saying that you might need to do it in 2 parts right here. So this concludes this first part of the video. In the second part of the video, I'll talk about what an object does when it goes up and down, and that might help you solve one of the problems. I think it's problem 14, which is meant to challenge you, so if it did, that's good. But I'll show you what you should be thinking or what could be done to do a problem like that. Okay? And I'll post these online. I have yet to post the other solutions, but I will as soon as I get to a scanner. Okay? I'll see you in the next video.